the case of a body of mass small m which is raised by height small h from the surface of earth without any acceleration, and we are interested in finding what is the change in potential energy of this body. So what we do is, if we take this as earth, mass is m and radius is capital R, we take this as first position and we take this as second position, which is at a height h from here, and this is certainly radius is capital R only, obviously. So if we raise this body without any acceleration from position number 1 to position number 2, so obviously there is going to be change in its potential energy, because we are saying acceleration is equal to 0, so it means there is not change of any velocity. It is almost a quasi-static process. When there is no change of velocity, there is no change of kinetic energy. So whatsoever the work we are doing, that gets stored as its potential energy only. So if we are to find the change in potential energy, that is delta potential energy, so it is potential energy at position number 2 minus potential energy at position number 1. So we know, and we also know, that is potential energy is minus gmm upon r between two bodies of mass m and m whose centers they are separated by distance r. So when we take the first case, so when we find PE2, for PE2 the gravitational potential energy is minus gmm upon r plus h, that is the distance between the two centers, and PE1 is equal to minus gmm upon r. So whether we say the work done or change in potential energy is going to be P2 minus P1 is equal to P2 is this minus gmm upon r plus h minus gmm upon r. So this comes out to be minus gmm upon r plus h, minus minus is plus, gmm upon r. So if we simplify it further, so this comes out to be delta potential energy, that is change in potential energy, is going to be, we can take gmm as common, gmm, so this is what, minus 1 upon r plus h plus 1 by r. So this is delta potential energy comes out to be gmm minus r plus h over r plus h into r. So this comes out to be gmm h over r plus h into r. Now we have been doing number of times, that is the substitution. When the mass m is at the surface of earth, radius of earth is capital R and mass of earth is capital M, then earth is going to attract this small mass m with the force, or we can also say that a small mass m is going to attract earth of capital M mass towards itself by a force, that is gravitational force, which is gmm by r square is equal to mg. The distance between the two is taken as r only, because the dimensions of small mass, they are negligible as compared to the radius of earth, which is 6400 km. So over here we say that is gm is equal to gr square. This substitution we have used number of times, we can put it over here also. So delta potential energy, that is change in potential energy when the body is raised from here to here, is gm is equal to gr square m h over r plus h into r. And if h is very small as compared to r, that is if h is very small as compared to r, the change in potential energy is going to be g r square m into h upon r plus h is r only, r into r. So this is r into r is r square get cancelled, so it is mgh only. So change in potential energy is mgh only when the h is very small as compared to r. And that is precisely what we had done in our chapter in work power energy, where we have used the conservation of mechanical principle also, and we had taken all the potential energy at the reference level or at the ground level as 0. So when the body goes from here to here, we directly say the change of potential energy is mgh, and that is the same thing what we are getting over here.